So I think we can start then, right? Hello, everybody, and welcome to the Tech Talk special new engine developments. My name is Markus Münz, and I'm with CIMAC. And I'm the host of today's meeting. I'd like to welcome all of you to these 4 really fantastic presentations we will hear today. We have some general things in the beginning, and then we will start the presentations. So first of all, with this Tech Talk special event, CIMAC would like to offer a platform for exchange only, and the presentations are an information offer to the respective authors and their companies, and thus they do not necessarily reflect CIMAC's opinion in general. Please be aware that this session will be recorded and you can view it on YouTube afterwards. And as an information also, you can type in your questions also during the presentation. So we have some questions to discuss at the end of each presentation. With this said, I can show you the agenda once again, and I'd like to hand over to Alexander Knaffel. He's from MAN Energy Solutions, and he will be the moderator of today's session.
Thank you, Markus. Welcome, good morning, good afternoon from my side. Now we are starting out with the first presentation. The presenter will be Francisco Lopez Gutierrez with Inyo GmbH, and his title will be Development of the Next Generation Gas Engine with Increased Efficiency and Reduced Emissions. Francisco, if you share your screen.
Sure.
You're good to go.
Can you see now my screen?
Yes, we can. You're good to go.
Okay, great. Then good afternoon, everyone. Thanks for the introduction, and thanks for giving me the chance to present today at the CIMAC Tech Talks. I will give you today a presentation on the latest developments on the Type 3 product, focusing on the development process and also the results that we have achieved with this latest development. This is the agenda for today. I will start with a brief update about the Type 3 product. What is the history? What are the applications? What are the main markets for this Type 3 product? I will move forward later on the technical developments on the Type 3 product, latest changes and developments we have been taking on this Inyo product around air handling, around the new cylinder head system, around the new valve train, power unit and combustion system, and the latest control measures that we have introduced to improve the reliability and the fuel efficiency and flexibility of this product. I will like to focus later on the development process as well, which are the key steps, will have been the key enablers to bring us to those results as well. And then I will finalize with a fact sheet on this product and the latest results on it. The Yamaha Type 3 product has a long history. We have a huge installed fleet from the 312, the 12-cylinder engine version with power output up to 635 kilowatts, electrical power output 316, the 16-cylinder version at 845, and the 320, which is the 1+ megawatt product that we have in our portfolio with more than 6,000 units delivered across the world. A standard product, as you can see. Yes, switch to the pointer. As you can see, bore stroke, it's at 2.44 liters per cylinder. It's a direct ignition combustion concept with a specific power output up to 18 bar BMEP, and the product is capable of 50 and 60 hertz. So a bit more about the history of the product. When the development of this product started, it was in 1988 with the A and B engine versions running at a slightly lower power output and a lower efficiency, but it started to cover already a wide variety of fuels, biogas, landfill gas, and that has been one of the strengths of this product, the fuel flexibility and the robustness to deal with a huge variety, as I said, of different fuels. Afterwards, we moved to the Type 3C, which is represents the biggest part of our installed fleet, covering as well a huge variety of fuels. 2013, we introduced the Type 3D, and next year we are serializing the Type 3F, the next generation of this product, increasing efficiency, increasing as well fuel flexibility, and reducing hydrocarbon emissions. On top of it, as I will mention at the end of the presentation, we will release as well the Ready for Hydrogen, Ready for H2 package together with this product. Moving forward to the technical developments and the product improvements that we have introduced here, we have developed a high-performance cylinder head. The development steps here have been starting from a 1D simulations, defining or deciding about the valve sizing and the port flow based on 1D analysis, and then coming to the right ratio of intake to exhaust valve diameter based on the 1D analysis, 1D simulations, and the port flow measurements. This has been the optimization path, the optimization way we have followed to reach the most efficient PMEP, the most efficient gas exchange. Beyond that, we obviously took some actions to understand skew angle, flow, port type to select the right trade-offs here with the design constraints, looking at the mechanical CDQs out of the FEA analysis, and on top of it, of course, optimizing swirl level, optimizing the flow ratio around the two ports of the 4-valve cylinder head. Beyond that, as you can see here, we went through optimization loop of the flow of the cylinder head by adapting the ports, and by means of doing that, we managed to increase the flow performance in average intake and exhaust by 30 to 40%, and that enabled that was one of the biggest enablers for the fuel efficiency increase on this product. All that was done by sticking to the same combustion concept that has been proven to be very robust and reliable for, as I mentioned, all the variety of fuels. We went through an additional development on the valve train and camshafts. We adapted, of course, the camshaft profile to the 4-valve cylinder head, to the introduction of a 4-valve cylinder head on this product. Wasn't available yet. And we went through an iterative process of performance optimization, mechanical analysis, and the final check of all the CDQs, of all the requirements. That has been the loops. Those have been the loops that we have been going through with the objective, with the target of optimizing gas exchange and volumetric efficiency, reducing hydrocarbon emissions, but also providing sufficient knock margin to enable higher, even a further increased fuel flexibility for this product. Since this is a well-established product in the market, one of the key focus was obviously to maintain reliability. This is why it has been one of the key development targets, focusing on the mechanical requirements and choosing the right trade-offs around that. Optimization variables have been obviously valve timing, valve lift to match the gas exchange, adapt the Miller timing, and the valve overlap to match or to meet the targets we had on this product on hydrocarbon emissions. On power unit and combustion system, we went through major adaptation of our combustion system and our bowl system by maintaining the same combustion concept. So therefore, we started with CFD analysis, trying to optimize the shape of our combustion bowl, as you can see in the right picture, by reducing the burn duration. That helped as well to increase the knock margin and also to reduce hydrocarbon emissions by having a shorter combustion duration. and ensuring that at the point in time of the exhaust valve opening, we had a successful combustion or a more complete combustion that reduces the hydrocarbon emissions. As you can see here, we went through major iterations, starting from a baseline concept and moving forward to a modified bowl shape that enabled to achieve those goals. Beyond that, we went as well a step beyond that in order to optimize the piston bowl shape for different compression ratios so that we could cover as well, or we can have a product that is optimized for the different applications in terms of compression ratio. In order to have an optimum solution for all those variants, we went through a loop of optimization as well on the aspect ratio of the bowl shape that enable an additional efficiency increase for those increased compression ratios, and therefore we could achieve as well an increased knock margin and an improved efficiency on those higher compression ratio versions. We went through that process, obviously, of iterations between the CFD and the single-cylinder engine testing, and the final optimization was conducted at the multi-cylinder engine at our development test benches to achieve this goal. Knock control and mechanical health are definitely a big benefit of this product as well. We introduced a state-of-the-art knock control system to enable an increased fuel efficiency and increased efficiency as well, and increase the fuel flexibility, and by means of introducing that, we also had a chance to introduce additional mechanical health features that enable as well condition-based maintenance, therefore enable service flexibility so that we can allow our customers to run or to plan their service interventions with more flexibility. Those measures are only possible because of the enhanced detection of the valve closure and the knock behavior. So we are allowed, or we can have more close or closer detection of the different events in the cylinder head, and therefore adapt our combustion chamber in cleaning intervals and lash settings intervals to those events. This is one of the big benefits of the system we are introducing now on the Type 3 product. I will go a little bit more in detail through the development process. As I mentioned before, the key or one of the key targets beyond the efficiency increase and the hydrocarbon emissions reduction was to maintain the reliability of this product, the well-established reliability, without compromising, obviously, the field flexibility that characterizes this product. Therefore, we leverage the tools you can see currently in the screen. So we started from a very detailed requirement document. We broke that down into all the different subsystems so that we had clarity for each of the different subsystems on the requirements and the test, the DVPNR, that is the design verification plan and report for this product. So at the end, we developed a test plan that was derived from the requirements and was derived from the risk management tools or from the FMEA. At the end, the FMEA plus their breakdown of the requirements to the subsystem level enable to come up with a solid test plan that was bringing us to the final successful results. We based that on the classical V model, making sure we have the requirements laid down and clarified for each of the subsystems, and that enables to go through all the systems case by case and requirement by requirement, and making sure we have full understanding and we have a clear validation path for each of the different subsystems. We went through a risk assessment process in every relevant milestone of the program development so that we tackle the FMEA of the different subsystems. And as you can see here as a schematic, starting with the risk rating for the different subsystems, for the different failure modes, we continuously de-rated the risks or brought down, mitigated the risk for each of the subsystems through the course of the development process. This is one of the objectives, and we achieved that by utilizing or leveraging all the different tools that we had in our hands, starting from analysis in the early phase, having a sufficient amount of front loading to de-risk the development later on, went through extensive phase of component test rig for cylinder head, valve train, and power unit. We went definitely an extensive phase of multi-cylinder engine that enabled a further de-risking and a further mitigation of the open risk or the open question marks in this product. And finally, we went through an extensive field validation and field inspection phase before final product release. As a summary of this product and this product improvement, we have introduced a flow optimized 4-valve cylinder head that enables fundamentally an improved gas exchange and an improved efficiency. We have introduced a new power unit that reduces hydrocarbon emissions by tackling crevice volumes and reducing hydrocarbon emissions by that means, and as well introduces a modified combustion bowl shape that improves the fuel efficiency and reduces the burn rate, therefore increasing the fuel efficiency as well. We have introduced as well a more service-friendly and improved valve train system that reduces the maintenance efforts to pretty much by 30 to 40%. We have introduced here as well as part of this product a modular and flexible coolant piping that enables more modular service activities on the engine as per needs. And we have introduced, as I stated before, a cylinder and lock control for improved fuel flexibility and condition-based maintenance. The new camshaft enables definitely an increased efficiency and a reduced hydrocarbon emissions by reducing valve overlap and optimizing the gas exchange tube. The key product highlights from the Type 3F are fundamentally an increase in electrical efficiency. So this package can be upgraded on existing fleet at any time. It can be ideally upgraded as part of a minor or a major overhaul of the existing units. Is ready for up to 25% hydrogen admixing without derating in the power, thanks to the knock control system and thanks to the improved fuel flexibility, to the increased knock margin of this new camshaft and new valve train system. And we have taken some steps as well to improve our CHP product, our CHP versions, increasing the overall electrical efficiency. And the same we have done on propane by increasing as well specific power output and electrical efficiency. As I mentioned before, we went through an extensive phase of component testing, in-house validation, running multiple overloads and durability tests together with all the functional tests from our DVPNR in-house. And we went through as well a very extensive field validation on multiple applications, on multiple fuels, covering the entire range of applications and fuels where the Type 3 product is exposed currently. As a major benefits of this product are an increase in electrical efficiency, an increase in total efficiency led mostly by the reduction of hydrocarbon emissions of around 30%, a reduction in fuel consumption driven by an improved power unit, reduces or that is able to deal with a reduced fuel consumption together with a new cylinder head, valve and seat material pair that is more robust and enables as well this reduction in fuel consumption. And together with new oil types that have been introduced with this product, with this package, the oil life is considerably increased so that it enables much longer oil life and a reduction on the cost, on the overall total cost of ownership on the lubricants. And having that as summary, I'm at the end of my presentation and happy to get your questions.
Well, thank you very much, Francisco, for the great presentation. Very clear, very well to understand. I'm just looking at the questions that have been submitted through the online tool. I don't see any right now. Maybe there's, it's a hiccup, or maybe to the audience, if you haven't done so, please submit your questions, and I would then, read them out loud and forward them to Francisco. Maybe one question from my end while we're waiting. You have mentioned 25% hydrogen with this product. And looking, further into decarbonization, are there also plans at maybe developing a version with even higher hydrogen rates? Have you considered that, or is that maybe in the planning?
Absolutely, this is part of the next development steps. We're looking at all our products and defining a path to increase the hydrogen capabilities of the product, and looking specifically increasing specific power output. As you know, we have the challenges of the knock margin and other inconveniences and other difficulties that come with the hydrogen development. But definitely, we are working on increased hydrogen portfolio for all our products.
Okay, well, thank you. I see there's one question now that came in through the chat. It reads, concerning the addition of hydrogen, did you see more NOx emissions when you run this blend of hydrogen and natural gas?
Not really. We have our control system. We have introduced now continuous monitoring of the NOx emissions, and therefore we adapt the operating point of the engine to match the requirements, to match the specific requirements of that specific engine version, meaning 200 milligrams, 250, or whatever is the requirement. Yeah.
Well, thank you very much. I don't see any further questions, so then thank you once again. And
thank you very much.
We will move on to the second presentation of today. Stig, are you in the line? If not, I would ask Mark Spani to present next. Mark is here. Mark
yes,
Spani,
I'm here.
With Winterthur Gas and Diesel, welcome. Mark will present new compact engines from WinGD tailored to the changing needs of modern vessels, applying latest innovations. Mark, we're looking forward to hearing your presentation.
I try to share my presentation.
We can see it.
You can see
it? Yes, now we can see the presentation.
Perfect, great. So thanks for the introduction, Alexander. Welcome from Winterthur. I'm working for Winterthur Gas and Diesel. Winterthur is sunny today, and I would like to inform you briefly about our new compact engines from WinGD, tailored to the changing needs of modern vessels, applying latest innovations. Quite long title. I shorten it a bit to make it crisper. I would like to present you WinGD's new XS engines. I have 3 parts in my presentation, rather simple. 15 minutes is not too long time. First of all, why did we develop the XS engines? Then why are they compact? That was one of the targets to have these engines, already to say now. And what is known technology-wise on the XS engine and what is new. I start with the first question, why new XS engines? To explain that, we need to go back a bit in time. The well-established X62 and 52 engines from WinGD, the development was initiated some 10 years ago. At that time, there was a clear trend to higher stroke-to-bore ratios to optimize engine and propeller efficiency. We had at that time ratios up to 5 in some cases. But nevertheless, beside these long stroke engines, there was a continuing demand for proven, more compact engines. In our case, this was mainly the Artiflex 50, D as a diesel and DF for a dual fuel engine. This remained, as there were still vessels with limited draft and limited engine room space. today we need to say that the fuel consumption of these RT-Flex engines is not competitive anymore. This is due to limitations in the maximum firing pressures. RT-Flex 50 was developed 20 years ago already, and therefore we decided to start the development of the XS engines, as we call them. It's still X, but the S stands here for shorter stroke. The XS engines are available in 52 and 62 centimeter bore, both as diesel and DF versions. I will not bore the audience too much with parameters, just a few words and two diagrams. You can see on the left side the rating fields for these two engines. Upper field is for the 52, lower for the 62 versions. The gray one is the XS and the blue one is the X engines. You can see the XS engines have a shorter stroke to bore ratio compared to the X types, and by that the whole rating field is moving to the right side to the higher speeds. But you can also see that the move from blue to gray is not exactly the same for the 52 and 62. This is due to the different applications. We tried to find solutions for both engines, covering the needs of the market, but not making the rating fields too big, but as big rating fields typically means also additional engine cost. The targeted market for these engines are vessels with low main deck height, low design draft, and small propellers. Some examples are mentioned here. The known X52 and X62B, they will remain in the portfolio, so we see the XS engine as a complement to the portfolio. And finally, the engine builders, shipyards, and owners can select whatever fits best to their needs. For the following slides, I will focus on the 62 version, as this is the one we developed as first. All what I say there is also valid for the 52, so don't worry if 52 is not mentioned anymore. First of all, I would like to go to the engine height and width in this chapter here. It is quite obvious if the stroke is reduced or the stroke to bore ratio is reduced that the engines get more compact. You see on the right side the cross section of the XS 62 in comparison to the 62 version. Height and width are reduced by almost 1 meter, and the piston dismantling height, which is relevant for the engine room height, is even reduced by more than 1.5 meters. The third dimension, there a bit more was needed to reduce also there the dimension. This is the engine length. First, we reduced the cylinder distance for these new engines. One of the two bigger measures or main contributors are the flexible girders. They are allowing more flexibility in the main bearings, so the main bearing can better adapt to the movement of the crankshaft, which cannot be influenced, and by that it was possible to reduce the width of the main bearing. And the width of the big end bearing is also reduced compared to the X engines by changing the shape of the connecting rod. You can see it here on the right side. This is the XS and this is the X, and here in the lower part there is more material, so the width here is getting bigger. We call it trapezoid shape, what leads to a better force transition from the firing force to the bearing, reducing the peak loads, and by that we were also able to reduce the width of the bearing shell here. Then also the driving end was optimized. We apply a small supply unit, very similar to what you know from the RT-Flex 50 already. By this we could reduce the sizes of the housings where the supply unit is attached. Then the gear wheels are reduced in size. First of all, I showed you the picture of the engine width. So the gear train needs to be shorter by obvious reasons, and also by applying this smaller supply unit, the width of the gear wheels could be reduced, and by this the length of the driving end section. Plus, we were also able to optimize the thrust bearing girders to a certain extent. This diagram shows then the result of all these efforts. You can see that for a 5-cylinder engine, the the XS62 is roughly 10% shorter than the X type, very similar in length as the old Artiflex 58T, but the XS62 has a power up compared to the 58 of roughly 15%. And the effect of all these improvements regarding height, width, and length are also well represented in the weight of the engine. So the XS type is about 15% lower in weight compared to a X type. The advantages of these more compact engines are, first of all, the easier accommodation in the engine room. This was also the main target of the whole development. Then the weight of the whole engine is reduced as shown, and of course also of many of the main components. This can possibly also reduce the crane capacity in the engine room. And last but not least, reduced engine cost obviously also means reduced material need, as the materials are still the same, so no exotic materials, just the standard materials, and by this we could reduce considerably the cost of the XS engines. There is no big disadvantage, on the other hand, on the BSFC, on the fuel consumption, as we still, with the XS engines, where we have a stroke to bore ratio of almost 4, we are quite close to an optimum. This is a bit above 4 maybe, but on the other hand, we have higher firing pressure with the XS engines than with the X engines, and by this it was possible to reduce the fuel consumption of the XS engine in comparison to the X engines by several grams over the whole load range. You can see here one typical example for 75% load. And by this, then finally, as I said, the shipyard engine builder and owner can select if they want to go for the X or the XS. X have maybe a bit advantage on the propeller side then. What is known, what is new from technology point of view? Typically, when we start developing a new engine, we are using concepts which are known from other engines. I show here some examples of the XS types. We apply the ICU, the injection control unit. I will show another slide on that then later. Known liner concept, I already showed the supply unit. Then we have the well-established jet shaker cooled piston with 2 piston rings, the built crankshaft, and the bed plate. So many things are known. This is also of advantage for the manufacturer, because they know how to produce these components. And of course, also from our end, we know how to design these components, because we have a huge number of engines in operation and a lot of experience on these components. Something that is new on the XS engine, not entirely new, but quite new, is the control system, the voice control system, which very much uses the concept of the known UNIC and VEX control systems, but using more modern electronic components. Every now and then you need to make an update on electronics with increased CPU power. We improved the user interface, and also the new control system enables remote monitoring. As I said, it's not entirely new. Since about 2 years, first 12-cylinder X92 DFs are in operation, and since then we started then rolling out the new control system to our whole portfolio. It's not yet concluded at the very moment. Then I already mentioned the injection control unit. This is a concept which was introduced more than 20 years ago on our very first Artiflex engines. It features a volumetric controlled fuel injection, and it has 3 rail valves. So each fuel injection valve on the cylinder cover is controlled individually, allowing for optimized control of the injection. There were several steps of improvements. That's why we call the current version also Mark 3.5, leading to an excellent service experience and long time between overhaul. We asked ourselves at the beginning if we go for the ICU or for the time control injector, and due to the pressure from the engine builders, we decided to go for the ICU because we have a well-established manufacturer base in Asia. The engine builders prefer this. Several manufacturers are able to produce these ICUs directly locally in Asia. And on the customer side, the ICU is well known for easy onboard maintenance, which can be done by the crew. Another novelty of the XS engines is the integrated SCR or the ISCR. Today's concepts have an integration of this T, we call it T-pipe here, plus a quite big SCR in the engine room. And our solution for this, at least for some of the applications, is the so-called ISCR, where we have the catalytic elements located right below the exhaust manifold. Of course, this offers a lot of advantages for shipyards and designers because everything gets more compact, no space is needed for the reactor in the engine room. The engine is delivered already with everything installed, tested, and integrated in the control system. And from technical point of view, the process temperatures are also higher because it's a short way from the exhaust manifold to the reactor. The compact design was possible by using catalytic elements with higher cell density and by limiting ourselves to SCR operation with fuels with low sulfur content. A very first ISCR is already in operation on an X52 engine, not exactly the same design, but very similar, to see how this whole concept is working in a normal marine environment. The next two slides show quickly how the SCR works, the ISCR, and how it looks inside. This is the tier 2 mode. The blue valves here, three valves are closed. Only the red one here is open, what means the exhaust gases go directly from the exhaust manifold to the turbocharger. When we go to the tier 3 mode, the red valve here is closed, but all the three blue valves are open. And then the exhaust gases have to take a bit longer path. They leave the exhaust manifold on both ends through these valves there. Then they go to the catalytic elements. They are marked here yellow in the lower part. Then the exhaust gases go back up again, and then finally also to the turbocharger. On the left side, you can see a small picture how this looks then on the engine with turbocharger and charging unit. The DF engines as such are not new, the DF versions. They are based on the well-established low-pressure gas concept. They feature two gas admission valves here in the mid-stroke area and two pilot valves, which are used to ignite the gas in the combustion chamber. What is new, not only to the XS engines, but to all the DF engines, is the ICER concept. This is our EGR concept for DF engines. Here we have, after the turbocharger, a back pressure valve, which controls the gas flow. About 50% in ICER mode go through this channel here, through the exhaust gas cooler, and then back to the compressor. The benefits of this is especially in gas mode, a more stable combustion, so we can better optimize the whole combustion process, what leads to an improved energy consumption in both gas mode and diesel mode. And as the gases are reused in the EGR concept, go through the combustion space again, there is also a considerable reduction on the methane slip, which is also more and more in the focus nowadays. With that being said, I've already come to my last slide, to the conclusion. So why did we develop the XS engines? These are engines for compact applications where space is limited. We developed 52 and 62 bore engines, both in diesel and DF variants. and they are complement to the existing engines in the portfolio. They are reduced in height and width thanks to the shorter stroke. They are reduced in length thanks to many optimization, leading to advantages regarding installation, engine weight, and production cost. I showed several components which are built on known principles. I showed some few new features like the ISCR, the ICER, or the device concept. And last but not least, we can report already first orders for the 62 variant of the XS engines. So the very first one will be on testbed somewhere by end of next year. And of course, more technology will come on these engines. For example, the variable compression ratio concept, VCR, and of course the engine will be also prepared later for all coming fuels. All about this and many other things we will then report in next year's CIMAC Congress in Busan, hopefully. And with that, I would thank you for the kind attention, and I'm giving back to Alexander for the question and answer session.
Well, thank you very much, Mark. Great presentation, great details. Let me just look at the questions. There's one question that came in. What is the share of pilot injection in DF mode? Can you comment on that? Maybe the amount of pilot that's required to, start ignition?
As far as I know, I'm not the specialist of engine performance, but as far as I know, it's around 1% of the whole energy that is brought to the cylinder is coming from the pilot. And of course, there is also a trend we try to optimize that, because basically we would like to burn fuel and not pilot fuel, or gas and not pilot fuel.
Well, thank you, Mark, for answering that question. There is a second one regarding methane slip, and the question is, do you have some numbers of methane slip, maybe in grams per kilowatt hour, or a unit that you are comfortable sharing?
No, I do not have this data available. Sorry for that.
Okay, well, thank you. Then there is another question. It reads, what about the maintenance of this engine? Would it be more tricky as it is a compact, it's referring to the XS as a compact engine design?
That can well be that in some areas the compactness gets a bit a disadvantage in that regard. That's a good question. At the beginning, I also had a slide in the presentation about the situation on the cylinder cover especially for the DF version. For a diesel engine, that's quite normal. We have the 3 injectors, but with the rather big pilot injectors, it's getting tight. And of course, the more close the components are together, can be that access to screws and dismantling some pipes can be a bit more tricky.
Well, thank you very much for answering that question. Also, that's the last question that came in through the chat. Well, then once again, thank you very much, Mark, and good luck with the further developments with introducing the new fuels. Thank you. And then we hand over to our next speaker, which will be Mino Merz. Mino, you're here already? Mino from Lund University, and the presentation will be on experimental optimization of a medium-speed dual fuel engine towards RCCI operation. Mino, we're looking forward to your presentation.
All right, I hope you can see my screen. Okay, yeah, thanks for the introduction. Very happy to tell a bit about the work that was done on a medium speed dual fuel engine, finding the balance between conventional dual fuel operation and RCCI operation. And a big driver for this kind of research, as we probably all know, is in the fuels. That's what we see in industrial applications, in heavy duty, but also in marine. We can get from different sources, we can basically get all kinds of fuels. through different processes. And yeah, the world is very interested in renewable fuels nowadays, coming from electricity and biomass. And also from these sources, you can basically make any kind of fuel, but yeah, the fuels that get most of the interest nowadays are these fuels: methanol, ammonia, methane, and hydrogen. That's where a lot of future developments are heading into. But what we also know is a large installed base of engines is compression ignited engines, diesel engines. It's not very realistic that all these engines are converted to spark ignited engines in a very short time frame, and for that reason there's a big interest in dual fuel engines in all kinds of markets. And the work that was done here was on a dual fuel engine using methane as the main fuel. It was done on a Wärtsilä engine. This engine is sold as diesel engine or as dual fuel engine, where the methane is port injected into the intake manifold. So it's pre-mixed, and just before top dead center, a small pilot injection is a small amount of diesel fuel is injected as a pilot injection, and this actually starts the combustion. What kind of engine are we talking about? It's a Wärtsilä W20DF, so it's a 200mm bore engine, 8.8 liter per cylinder. We did all the tests at 900 RPM. It can run 200 bar peak pressure, 4 valves per cylinder, and this experimental setup at Lund University is running electrohydraulic valve operation. So basically we have all kinds of freedoms to operate intake and exhaust valves with variable lift and timing. Completely cameless test configuration, which is very nice for experiments. For this experimental setup, the engine is also equipped with a common rail. We can go up to 2,300 bar. For this test, the pressure was not that high. As I said, it's a combination of diesel fuel and natural gas, where we did run a global lambda of 2, which seemed to give the best results. Let me tell a bit about the trigger of this research. Why was it done? Someone who worked on this engine before me came with a quite interesting relation between pilot timing and start of combustion timing. When we look at the right side of this graph, so from -30 towards top dead center, we see typical diesel engine behavior. When we go to earlier injection, we have earlier combustion, which is very common. That's what you would expect. But at a certain moment, the relationship changes, and a further advancement of the pilot timing results in even this area leads to a further retarding of the start of combustion. And what we can say, this first phase, this is typically conventional dual fuel, same behavior as a diesel engine. And what we see in this even more advanced timing, that it starts to run in RCCI mode, so reactivity controlled compression ignition. That's a typical low temperature combustion system, where with very strong dilution of your pilot fuel, you reduce temperature, you reduce reaction speed, which can be very beneficial for NOx production and efficiency. But we wanted to have a better understanding why and where this relationship changes and what are the effects on it. To find that out, basically 3 different campaigns were run. The engine was run in optical mode, so it was converted to an optical configuration, a boat edge mode with a glass piston, where with a high-speed camera we could really look into the combustion chamber. Then we did on the metal engine a set of emission measurements, and that's the main part of the results that I will present later on. And based on the optical research and the emission measurements, a conceptual model was developed that explains this relationship between what you do with your pilot and when the combustion will start. But let's continue on the emission measurements that were the bulk of this talk. The goal was here to find data, to have optimal test points for the optical research, to find out where we could find the best behavior, and also to improve the understanding of what is happening, how is this pilot injection igniting the combustion, and what are the results. A small sidestep on this optical research, as I already mentioned, RCCI results in strong dilution of the pilot injection. So an interesting question is, can we see that this happens? Yeah, we can see that. What you see here in the top left corner is the view through the glass piston into the combustion chamber. And we can make recordings for every individual combustion cycle and record visible light coming from the combustion. And when you look at this graph in the left lower corner, there we see the recording of light during the combustion cycle. So here on this axis, we go through the combustion cycle, top dead center, and then position after top dead center. And when we follow this arrow, so we rotate through the combustion chamber, there is this angle here between -180 and +180 degrees. So we follow the complete shape of the combustion chamber. There we can clearly recognize these 9 individual peaks, which are the jets of the diesel injector. So what we can clearly see in pure diesel combustion, and the combustion takes place around the diesel jets. When we go to conventional dual fuel, that's the upper right graph, there we see more or less, we can still recognize these 9 different jets. The pilot injection is very small, so there starts to become some deviation between the 9 jets. The intensity is much lower, but still, you can see that in this conventional dual fuel mode, combustion is taking place around these jets. That is where the high intensity of light of combustion is taking place. And when we go to RCCI mode, so the mode with this very early injection there, these 9 jets are not more recognizable anymore. The light is occurring quite random through the combustion chamber, a little bit more intensity towards in the area of the exhaust valves, because we have a bit more temperature over there, but no jets recognizable anymore. So that means we have a very strong dilution of the pilot fuel. The whole idea of this strong dilution is that it reduces peak temperature, and for that reason it reduces NOx emissions. Well, can we recognize that in the emission measurements? That's what you can see in this graph here for a medium load case. This was a reference load of 14 bar IMAP. There you can clearly see the gold brown line. That's representing NOx emissions in grams per kilowatt hour, indicated that once we go in that early area, NOx significantly drops off. So we can go to very low NOx emissions by strongly diluting this pilot injection. And that's where we reach NOx emissions below 100 ppm. Serious reduction. While when we go to the more diesel-like timing, we can go to very high NOx emissions, and once we retard more than that, NOx drops off again. And that's what we know, of course, from typical diesel engine behavior. The emission of uncombusted hydrocarbons, which is important when you run on natural gas or on methane, because it's a very strong greenhouse gas, it has more or less the opposite behavior. So in this area where you have high NOx production, you have the lowest hydrocarbon emissions. And once you go to very strong dilution of the pilot, so very early pilot injection, the emission of hydrocarbons start to increase again. Mainly this dilution reduces temperature, reduces the complete combustion of methane, and the same is happening in the very late area. There you are late in your combustion cycle with the bulk of combustion. Piston is going down again, temperature is decreasing already. There are less favorable conditions for methane combustion. What you could also recognize on this graph that we have limited testing points here in the middle, and there's a clear reason for that. When you run into knock problems, it is limited by knock, and since it was not part of this research, we didn't go for the highest. We didn't try to go as close to the knock limit as possible, so we just skipped this tested measuring points. At the lower engine load, around 10 bar IMAP, we see the same behavior. The difference is that it is not knock limited anymore. So here we can do measurements over the complete range. We see that NOx is peaking even more in this intermediate range, but also here, when you go to very early pilot timing, NOx can get extremely low. The same is happening on a high load case. This was 18 bar IMAP reference, but here it was basically everything later than this RCCI timing range was knock limited. So not so much information could be taken from this operating point. So this is emissions. That's of course only part of the story. We're also interested in efficiency and phasing. There you see more or less the opposite as with the previous graph. Efficiency, the golden brown line. Let's have a detailed look at the medium load case. Highest values can be found in this early timing range. So RCCI, with this lower temperature and for that reason lower heat losses, has an advantage over here. When you go earlier, efficiency drops off again, mainly because your combustion phasing, which is represented by the blue line, is too late, so you may taking less effective work out of your process, so that's why it drops off again. And the same happens when you go to conventional dual fuel operation, where the late timing results in the end in late start of combustion and late CH50, so late midpoint of your combustion process. And also here for low, medium, and high load case, we see the same trends happening. An interesting point in medium load is here, this small drop in efficiency. Initially, when you go from very early to later, efficiency increases mainly because you are combusting more of your methane, so uncombusted hydrocarbons go down. But at a certain moment, it drops again because you are having your CH50 below 0 crank-angle degrees. So the combustion process is happening really too early, creating negative work at the beginning of the combustion process. What was also interesting to notice is that cycle-to-cycle variations was quite significantly dependent on pilot timing. Where in this mid-range, where you typically have the highest temperatures, you have the lowest cycle-to-cycle variation. And when you go to very early pilot timings, it increases. And when you go to very late pilot timing, it also increases. And we found out it has more or less the same behavior as uncombusted hydrocarbons. So when you're on an experimental engine where you're not able to do emission measurements, for example, in an optical engine, because it runs in skip fire mode, you could use cycle-to-cycle variation to have an indicator on how complete your combustion is. Reasons for these high uncombusted hydrocarbon emissions is on the late side, it's too late combustion, so at low temperature, and on the early side, it's too strong dilution, so the complete mixture is too lean. Your pilot injection is diluted too much, and that's not beneficial for your stability of combustion. Let's combine all the results that we just saw For the medium load case, looking at NOx, hydrocarbons, and COV IMAP, yeah, we can clearly see, of course, it depends a bit on what your requirements are, lowest emissions, lowest efficiency, or yeah, we have some generic requirements. We could conclude that in this RCCI timing range, so around minus 45 degrees crank angle, we have the best overall results. So yeah, that's where you combine low emissions with high efficiency at a reasonable COV. Depends a bit on application, what COV is acceptable. Yeah, we did look at a range from 3 to 5% as being an allowable amount of variation. So now we know where to go in the next optical campaign. As mentioned before, this RCCI mode is known for low NOx. Can we recognize that on the combustion profile? So we compared two pilot points, one with RCCI, one with CDF. Significant amount of difference in NOx productions, 1 gram per kilowatt hour and 5 gram per kilowatt hour. This is the typical bell shape of heat release rate coming from the RCCI combustion. Quite different than conventional dual fuel combustion, where you can clearly see the initial heat release peak of the pilot combustion. And the interesting thing is, surprisingly, could be a surprise that the RCCI mode has a higher peak in heat release, but the conventional dual fuel mode has this peak much earlier. That means it happens in a small volume, and it happens at a higher intensity. If you want to, in this small volume, create the same amount of heat release, it means you are creating a lot of temperature, and you're creating the temperature very early in the process. So that will mean that the total process temperature will go up during the combustion. And that gives an explanation of why this NOx production is so much higher in RCCI mode. I'm aware that this time slot was a bit limited, so it was probably a bit condensed in results, but hopefully we still have some time for questions, so feel free to ask.
Well, thank you very much, Mino. Let me just briefly look at the chat if there are any questions. I don't see any yet, so maybe let me ask you one question. You've nicely pointed out that challenges with HCCI, which are really two things, I believe, which is controllability on the one end, and which is high loads, or basically the lack of being able to achieve high engine loads. Have you had any thoughts on how to maybe extend the high load range, to also get the benefits of quick combustion, low NOx, good efficiency, low hydrocarbons?
Yeah, that's a very interesting question. Basically, everybody is looking for HCCI, and this RCCI mode seems to be already the most feasible way to run a low temperature combustion. What you can do is we were not completely not limited or high load limited. Especially on high load, it was better to run in RCCI mode than in conventional dual fuel mode. So there is already an advantage over there by this combustion mode. What can be done is go to even leaner mixtures in this high load operating range. So you can go to a global load, so it's air, diesel, and natural gas. Around lambda 2.2, 2.3 there. That can be done to reach higher loads. One other thing we did some experiments with, but that's not very feasible for production engine, is play around with valve timing. So because we were completely variable on this engine, more spooling of air, more cooling of the combustion chamber with excess air, that could help a bit.
Okay, well, thank you. Thanks for answering that question. I don't see any questions in the chat, so then I would like to thank you once more for the nice work and the great results that you've achieved. Thank you, Mino.
Okay.
Then we're back at the agenda. Now, I'm wondering if Stig Jakobsen is in by now, if he had a chance to dial in, or maybe someone from the CIMAC organizers can comment if you've reached Stig, if he's still available.
So I couldn't reach him, unfortunately, and I cannot see him in this meeting right now. So I think we have to end it then.
All right.
So,
well, thanks to the audience, thanks to the presenters. It was a great session, great insight on the developments. And like Marcus had said, there is another session scheduled, which we are all looking forward to.
yes, I can just have one more slide. So, yeah, thank you, Alexander, for this comment, and you're moderating today this tech talk. And also, I would like to thank all the speakers of today's talk. It was really interesting and nice presentations. And like Alexander just mentioned, there will be the next tech talk on Tuesday, 11th of October, same time. And the topic will be the engine components. With this said, we can end today's meeting. I thank you all for your time, and we're looking forward to see you on the next tech talk. Thank you.
Thank you. Goodbye.
Goodbye.